Today we are going to state and prove the Myhill Nerode Theorem. And before we state the Myhill Nerode Theorem, which is going to use refinement, we need to know what is refinement between relations. We can try to understand with an example. Consider the binary relations R1 and R2 on this set, and here R1 is defined as this: A is related to B if and only if A is less than B. You can verify that it is true for every pair, and these are the only pairs satisfying this equation. And R2 is defined as A is related to B if and only if B is nothing but 2 times A, and these are the only pairs. So relations are clear. Now can you see any relationship between R1 and R2? You can see that every pair in R2 is also in R1. That is, for all pairs AB, if AB is in R2, then AB is in R1 also. So whenever A and B are related by R2, it is also related by R1. This is a property satisfied by these two relations. Or equivalently, we can say R2 as a set of pairs is a subset of R1. So every pair in R2 is also in R1. And then R2 is said to refine R1, that is refinement. When the relation R2 as a set of pairs is a subset of R1, then R2 is said to refine R1. Or whenever A is related to B under R2, if we can prove that A is related to B under R1, then R2 refines R1. See a more interesting example. Two relations are given on the set of natural numbers. R1 is defined like this: A and B are related, A related to B, if you get the same remainder when you divide A and B with 2. And R2 is defined as A and B are related when you get the same remainder when you divide A and B with 4. It is not difficult to verify that R1 and R2 are equivalence relations. For the interest of time, we are not doing it now. You can verify it offline. Now assume that they are equivalence relations. It is easy to observe that the equivalence relation R1 induces these two equivalence classes. This is the set of all natural numbers giving 0 as the remainder when divided with 2, and the other class is those numbers giving 1 as the remainder when you divide with 2. So any two elements in this set and any two elements in this set are related. So it tells you that the set of all natural numbers is partitioned into two sets by the first equivalence relation R1. Similarly, you can see that the second equivalence relation R2 partitioned the set of natural numbers into 4 equivalence classes corresponding to the remainders 0, 1, 2 and 3. That is, when you divide with 4, the remainders can be 0, 1, 2 or 3, and those numbers giving 0 as remainder are coming in this set and similarly in the other set. And if you carefully observe, you can see that the first equivalence class induced by the relation R1 is subdivided into 2 classes by the relation R2. That is, the set of all even numbers here is partitioned into 2, one for remainder 0 and the other for remainder 2 when you divide it with 4. Similarly, the odd numbers This is the single class here is subdivided into 2 by this relation. Okay, R2 is inducing 4 equivalence classes, and you remember that these 2 classes are subdivisions of this single class induced by R1, and these 2 are subdivisions of the single class here, and here you can verify that R2 is a refinement of R1. That is, whenever 2 elements are giving you 0 as the remainder when you divide it with 4, it will also give you 0 as the remainder when you divide it with 2, because 2 divides 4. So for these 2 classes, you will get 0 as the remainder. So whenever 2 elements are related here, the 2 elements must be related in this relation as well. And that is always true, because here the equivalence classes are partitions of the equivalence classes here. If these 2 are here, that means these 2 must be here, because the same equivalence class is subdivided into 2. You have not done anything else. So when an equivalence relation R2 refines another equivalence relation R1, then actually R2's equivalence classes are subdivisions of the equivalence classes in R1. If you can please remember this fact, when R2 is an equivalence relation refining another equivalence relation R1, the number of equivalence classes of R2 refines R1, is more than that of R1. That is, whenever R2 refines R1, where both R1 and R2 are equivalence classes, then R2 will contain or will induce more number of equivalence classes. This is a very important property that we need to use later. Now we can formally define refinement. A binary relation R2 on a set A is said to refine another binary relation R1 or A if for all pairs xy, xy is in R2 implies xy is in R1. That is, x is related to y under R2, then x must be related to y under R1. If all pairs satisfy this relation, then R2 is said to refine R1. Now let us recollect what we learned as Myhill Nerode relation. This is what we learned. It is an equivalence relation which is a right congruence of finite index refining a language. I hope you remember it. This is what we discussed in the lecture L22. If you don't remember, please go back and see that this is what we learned. Now we can see a relationship between Myhill Nerode relations and DFAs. This also we have discussed in lecture L23. Suppose you take a DFA. By applying the algorithm that we discussed in the lecture L22, we can get an MN relation. And on this MN relation, if you apply the algorithm or construction that we discussed in the previous lecture, you will get a DFA. So we started from a DFA, ended up with a DFA. And we also saw that these 2 DFAs are isomorphic. Or you can even start with a Myhill Nerode relation. If you apply this construction, you will get a DFA. Then on that DFA, if you apply this construction, you will get an MN relation back. So started with an MN relation, ended up in another MN relation. You can prove that these MN relations are identical. Identical means x is related to y under one relation if and only if x is related to y under the other relation. So in terms of refinement, when they are identical, this refines this and this refines this. So it's two-way refinement. It's called bi-refinement. Now we are coming to a more interesting equivalence relation on the set of false strings on a language, set of false strings of an alphabet set. And later we will state and prove Myhill Nerode Theorem, which is utilizing this canonical equivalence relation. I am giving you the definition. Let L be a language. It can be regular or non-regular over an alphabet set sigma. Note that this is an arbitrary language, need not be regular. And you consider the equivalence relation denoted as equivalence relation induced by the language. Okay. X is related to Y under this equivalence relation if and only if for all strings Z, all strings including even X and Y. When you append the string Z to both X and Y, you will get XZ and YZ. Both are in the language or both are not in the language. This is the property that X and Y should satisfy for all strings Z. Then you can say that X and Y are related set. That is, for all strings Z, if appending Z to both X and Y gives you strings both in the language or both not in the language, then you can say that X and Y are related. You can prove that this relation is an equivalence relation. We need to prove that it is reflexive. That is very easy and trivial. We can prove that for all Z, XZ is in the language if and only if XZ is in the language. That is trivially true. LHS and RHS are same. Then if you apply this definition, XZ is in the language if and only if XZ in the language is what we are getting. That is, X and X are related is what we are getting. So it is reflexive. Now we need to prove that it is symmetric. Assume that X is related to Y under this relation. Then from this definition we have for all string Z, XZ is in the language if and only if YZ is in the language. This is if and only if. So we can interchange the LHS and RHS because equivalence relation. This is equivalent. So we are interchanging, and now if you look at this and the definition of the relation, you can easily observe that Y is related to X. If you apply this, you have to get for all Z, YZ is in the language if and only if XZ is in the language. So we proved that it is symmetric. Now we are going to prove that it is transitive. Suppose X is related to Y and Y is related to Z. Then applying this equation we will get for all strings W, because we have X, Y and Z here, W, if you append the same string W to both X and Y, one is in the language if and only if the other one is in the language. Similarly, when you apply it over this pair, you will get YW in the language if and only if ZW is in the language. If we combine these two, you can easily see that you can say for all W, XW is in the language if and only if ZW is in the language, because this if and only if is transitive. So this tells you that by this definition X is related to Z. That is, we assume that X is related to Y and Y is related to Z. Then we prove that whenever this is true, X must be related to Z. So we proved that it is transitive. Hope you followed. Otherwise, please watch it again. For the interest of time, we have to proceed. So we proved that it is an equivalence relation. You can also prove that it is a right congruence. Right congruence means whenever X is related to Y, XA must be related to YA for all simples A in the alphabet set. We can prove it in different ways. Now I am attempting to prove it using contradiction. For the purpose of contradiction, assume that X is related to Y, but XA is not related to YA. Not that I have not written X related to Y here, but I am taking it from here. assume that x is related to y, but xa is not related to ya. And why xa is not related to ya by this definition? That means there exists an z such that when you append z to both of these strings, one of them is in the language and the other one is not in the language. Doesn't matter which one is in the language. Suppose when you append the same string to both these, from the resulting strings, one is in the language and the other one is not in the language, then they cannot be related. That is the only case they cannot be related. Okay. Now you call AZ as W, then you can say that you just call AZ as W. That is what I did. Call AZ as W. Then it can be written as XW and this can be written as YW. And see what you are getting here. There exists a string W such that when you append the same string W to X and Y, you are getting XW and YW. Such that one of them in the language and the other one is not in the language. So if you look at the definition of this relation, you are getting that the existence of this W as a string is telling you that X is in fact not related to Y. So it is a contradiction that X is related to Y. So whenever X is related to Y, XA must be related to Y. So we proved that it is a right congruence. We can also prove that this relation refines the language. We have to prove that whenever two strings are related, then both the strings are in the language or both are not in the language. We can prove it. Assume that X is related to Y. Then by this definition we have for all string Z, XZ is in the language if and only if Y is in the language. What is Z? Z can be any string. Substitute Z as the null string, you will get X followed by, I am substituting Z as null string, that is X followed by null string, that is X itself, in the language if and only if Y null string, that is Y, in the language. That is X is related to Y implies both X and Y are in the language or both X and Y are not in the language. That means the relation refines the language. That is the definition. Thus, the canonical equivalence relation for a language satisfies all properties of an MN relation except the finite in-text property. The number of equivalence classes is finite or not, that we don't know, or by using the property of this relation you cannot prove it. So that is the only property of an MN relation which is not satisfied by the canonical equivalence relation for the language. So try to remember the canonical equivalence relation. It is a right congruence, okay? It's an equivalence relation. It refines the language. And what is the definition? Two strings X and Y are related if and only if for all strings Z, if you append Z to both X and Y, either both the resulting strings are in the language or both are not in the language. Now we can see a very interesting relationship between the canonical equivalence relation for a language that we just defined and MN relations. When we are going to talk about MN relations, we may be discussing about only regular languages. But remember, the canonical equivalence relation is there for all languages. But here we are only looking at regular languages. Let L be a language over sigma and this be an arbitrary MN relation for L. See, there is an MN relation for L. Then from lecture 23 we know that it is a regular language. Okay. So we are given with a language, an MN relation for that language, and you also consider the canonical equivalence relation for that language that we defined in the previous slide. then theorem claims that the arbitrary MN relation for the language must refine the canonical equivalence relation. That is, whenever two strings are related by the MN relation for the language, then they must be related by the canonical equivalence relation for the language. And that is why this relation is named as the canonical relation, because any other MN relation for that regular language will refine it. We can prove it. Suppose that x and y are related by the MN relation. Now, by utilizing the right congruence property of the MN relation, we can prove that for all strings z, xz is related to yz by the MN relation. Why? Because it is right congruent. So, whenever x is related to y, xa must be related to ya. Similarly, you can extend for all simples in z and you can prove that xz is related to yz. Now, if you apply the refinement property of the MN relation, that is this property, the MN relation refines the language. You know that whenever xz and yz are related, then either both are in the language or both are not in the language. And this is for all z. Now you carefully look at what we are saying here. For all z, when you append z to both x and y, then the resulting strings are both in the language or both not in the language. This is exactly what is defined as the canonical relation. So we are getting that x and y are related by the canonical equivalence relation. So we assume that x and y are related by the MN relation for that language, an arbitrary MN relation for that language, and we prove that then they must be related by the canonical equivalence relation. That means whenever x and y are related under the given Myhill Nerode relation, whatever be that MN relation, they must be related by the canonical equivalence relation for the language. So we are done. This is from this definition of this relation. And now you recall that when a relation refines another and when both are equivalence relation, the number of equivalence classes induced by this relation must be more than the number of equivalence classes induced by this. This is what we know from refinement. Now this is an MN relation which is having only finitely many equivalence classes, and because it refines this for this language, the canonical relation must be of finite index. And using that property, you can have a corollary. If you apply the algorithm that we discussed in the lecture L23 to construct a deterministic automaton from an MN relation, you will get the unique minimal automaton for a language if you apply it on the canonical equivalence relation. If the language is regular, then there must be an MN relation for the language, and from this theorem we know that the MN relation must refine the canonical equivalence relation, and therefore the number of equivalence classes here must be greater than or equal to the number of equivalence classes of this. And we already know that an MN relation will have only finitely many equivalence classes. So for a regular language, the canonical equivalence relation will have only finitely many classes. And why is it that this is a corollary? Because if you take any DFA, that will induce an MN relation, and that MN relation will refine the canonical equivalence relation. And what about the number of equivalence classes? Here the number of equivalence classes of that induced Mn relation will be the number of states in the given DFA, and that will be more than the number of states in the DFA that you obtain by applying the construction on the canonical equivalence relation. It's a little difficult thing, but I think you are getting, or you watch it again and see why this corollary follows. And you can have another corollary which tells that when the language is regular, this is going to have only finitely many equivalence classes, or it will satisfy that property as well, and hence it is an Mn relation. It's because when L is regular, there exists an Mn relation, and by this theorem that Mn relation refines this, and then from the refinement this will have less number of equivalence classes than this, which is having only finitely many equivalence classes, and hence corollary 2 follows. Now we can state and prove the Myhill Nerode theorem, and this is the theorem. If L is a regular language, if L is a language over an alphabet set, then the following 3 statements are equivalent: saying L is regular, or saying that there exists an Mn relation for L, or saying that the canonical equivalence relation is of finite index. All these are equivalent statements is what the Myhill Nerode theorem is claiming. We can prove it, not difficult. We can prove that if L is regular, then there exists an Mn relation. This is what we did in the lecture L22. We discussed an algorithm which will give you an Mn relation from a DFA. So whenever 1 is true, 2 must be true. Now look at this implication, that is, whenever there exists an Mn relation, then the canonical relation is of finite index. This is what we proved in the previous theorem. In the previous theorem we proved that if there exists a Myhill Nerode relation, then it must refine this canonical equivalence relation, and from refinement we know that if this relation refines this, this will have more number of equivalence classes, which is already finite. So this is done, and finally whenever the canonical Myhill Nerode relation is of finite index, L must be regular, because if you apply the construction that we learned in the lecture L23, you have a Myhill Nerode relation now, because it is the canonical equivalence relation which is now having only finitely many equivalence classes, so it is an Mn relation. Now you apply that Mn relation to DFA construction, you will get a DFA, and because you are getting a DFA for this language, we are done. L is regular. So we proved the Myhill Nerode theorem, which is a very nice theorem having a number of applications, which tells that saying L is regular, or there exists an Mn relation for L, or the relation, the canonical equivalence relation is of finite index, all these 3 are equivalent statements. Today we learned about refinement between relations, a canonical equivalence relation on the string set for any language. Then we proved the Myhill Nerode theorem. There are a number of applications for Myhill Nerode theorem that we may discuss later. Thank you.